Hey everyone, welcome to this lesson. It is part 2 of lesson 6.1 for pre-calculus in our Math 176 course. And part 1 has already covered a couple of these topics here. The first two items we've pretty much nailed those down. So those are done. Actually, the skill builder is done also. If you watch the YouTube recording of lesson 6.1 part 1, you've got that skill builder practice as well. The last part of this, the second part, is going to cover exponential functions base E, something called continuous growth and decay, and the compound interest formula. Those are three big subjects that we're going to cover in this lesson. So let's scroll down there. And actually, I do have one more lesson slide here that talks about exponential functions in general. So this is actually a little bit before we do the exponential function base E. It's kind of like the last thought in just the standard exponential function. And it's a study in how do you compare the difference between a linear equation and an exponential equation. Now in chapter 4, we got really good at studying linear equations. But here's a bunch of numbers, and they're asking us questions like, okay, which one's linear and which one's exponential? Now, things to remember: linear functions grow by adding. The slope increases the y value each time. So you're adding a little bit, you're adding a little bit, you're adding a little bit. So exponential functions grow by multiplication. So these grow by add. Whereas exponential functions are going to grow by multiplication. So we have to multiply each time. Now we're going to use some analysis of these numbers to figure out which one is which. Now when we're studying tables and data and numbers, first notice the x. Now this analysis can be really hard if the x's are random. Like if it went 20 and then 22 and then 29 and 33 and 56. We don't have a very nice increment because it's kind of randomly stepping from each one here. But here, all the x's have the same increment. We are increasing by 5, and that helps our analysis quite a bit. So one of the things we would be looking for if we were looking for a line is a constant rate of change, which means the slope is going to have to be the same number for all the pairs. And so we have to look at the pairs. Let's take these two pairs. This would be like x1, y1, x2, y2, and then we could explore the slope of this. I'm going to put the slope formula up here. You remember y2 minus y1, x2 minus x1. And so in this data table, the x's are easy. 25 minus 20 equals 5. The top is 45 minus 30, which is 15. And that turns out to be a slope of 3. So is it 3 every time? If it was constantly 3, then we'd know that the f function is linear. But we don't know until we check several of them. Now, here's the shortcut. And the shortcut comes to us because the x's have this constant increment. If we look at these 2 points, the difference is 30 minus 25, which is 5 again. So I'm going to have 5 every time. So if I'm going to do the slope, I'm going to divide by 5. So when I do my study of this, because I have nice x's, I am going to concentrate on only the change in y. So we call this delta x. Delta x equals 5 every time. I don't have to worry about that. So if delta y has a constant change that's the same in every pair, then I know it will have a regular constant slope. So what I'm going to do as a shortcut is just look at the y's. 60 minus 45. If I do y2 minus y1, I get 15. Hey, that's the same as the first one. If I do these two, 75 minus 60, oh, that's 15 again. Now, I did 3 in a row, and 3 in a row are coming out with 15 over 5, which comes out with the slope of 3. It's like every single time 3 in a row. That's pretty likely that it is linear. Now, maybe the data isn't perfect, and if we checked a few more, we might see some anomalies here. But I think we can jump to a conclusion here because we've done 3 tests and we found the slope was 3. So I think, we could check a few more. 90 minus 75, that one's also 15 again. All right, so I've come to enough data that I can reasonably draw my conclusion here. And I'm going to call it F is linear. What about G? Is G linear? Well, let's do the same analysis on G. Now, if it's linear, we have to look at the slope. Okay, but the x's are always going to be incrementing by the same number. So I'm going to shortly go to the shortcut here. So if I did 1,200, that's y2 minus y1 over 25 minus 20. That equals 5. So what we're discovering here is this is called delta y, delta x equals 5. So it's going to be 5 every time because the x's are counting by 20, 25, 30, 35, 40. They're counting by 5. So that is going to be redundant. I don't need to do that calculation over and over again. So I'm going to check just the delta y. I'm only going to see if the delta y comes out the same every time. So the first time, I get 200 for delta y. The second time, now I'm going to move my points over. And I'm going to use this pair, x1, y1, and this pair, x2, y2, and try again. Now, I'm only going to look at delta y. It is 1440 minus 1200. That's the delta y. And when I subtract that, I'm getting 240 equals delta y. Now I see with my first try and my second try that the change in y's is different. So if I did the slope, I'm getting a different slope on this second pair of points, which is suggesting to me strongly that it's not linear. I think I'm going to do just one more check to make sure. And so this time, I'm going to do the next pair and see if I find the slope on this next pair, if it works. So it's like x1, x2, y1, y2. And we don't have to do the x's because we've figured out the shortcut there. The x's are always counting by the same. Now that doesn't happen on every table, by the way. So we can't take this for granted. This is nice that all these x's are counting easily for us. But on my third pair, I'm going to find delta y. So I'm going to subtract 1728 minus 1440. And then when I do this calculation, 1728 minus 1440, I get delta y equals 288. Every time the y number is different. I said that wrong. Every time the change in y is different. So if I did the slope for all three of these pairs, since the change in y is different each time, the slope is not the same for the function g. So what we can conclude here, because we don't have the same slope for each pair of points, that it is not linear. Okay, now remember I said that a linear function grows by adding, and I don't know if it's linear until I look at the slope. And so I'm basically working backwards from the points to find out if it's linear. Well, if it grows by adding and I'm working backwards, I have to subtract. And that's what I'm doing. I'm subtracting the y's. Okay, so g, it's not linear. Now that does not mean it's exponential though. So it might not be exponential either. How do we know if something is exponential? It grows by multiplying. It has to have a constant multiplier. So what I want to do now is look at the g numbers and see if there's a multiplier. So on g, now we're going to look for the possibility of a constant multiplier. That means when I go from one y point to the next y point, I have to be multiplying by something. And it has to be the same multiplier every time. So it's like, what could I multiply to 1,000 to get 1,200? Question mark. Well, if I took 1,000 times a number b, I have to get 1,200. So I'm trying to figure out the b that's my multiplier. Well, what's the easiest way to find the b? Well, that would be to divide. I have to work backwards. Since I have the points and I'm trying to find the multiplier, I don't know what the multiplication is, but if I divide the y parts in the points, I can see the multiplier. So if I take 1,200 and divide by 1,000, I get 1.2. So that means my multiplier is 1.2. I take 1,000 times 1.2. Now, is that the same multiplier for all of them? I don't know. I have to check them all. And if it is the same multiplier for all of them, then that means it's an exponential function. That I have a base and I just take that base to a power, another power, another power. So how do we check? Well, we're going to do to see if I have the same multiplier. Question mark. What's the shortest way to find that multiplier? Divide the numbers. I'm going to take 1440 divided by 1200. And you put that in your calculator and you discover, hey, it is 1.2 again. So 2 times in a row, when I take the y coordinates and multiply by 1.2, I get the next y coordinate. So let's make sure that that works even further. So I'm going to try it again and see if it continues. What's my multiplier? Question mark. So I'm going to take 1728 over 1440. Now that one's not as easy to multiply. Let's bring the calculator up here. I'm going to change the view really fast. Should have done that. Okay, you can see I pulled up the calculator here. I'm going to divide the 1728 by 1440, and I get 1.2 3 times in a row. So what this is telling me is if I take the first y number, 1440, and times it by 1.2, I'm going to get the 1728, the next number. Does that keep happening? Well, let's do the next one. And since I got the calculator up, I'm just going to do the division in the calculator. 2073.6 divided by 1728. And I get 1.2 again. So this is like 4 or 5 times in a row. This problem has a constant multiplier. So I have a constant multiplier. So I'm saying I have a constant multiplier of the 1.2 each time. Now that constant multiplier is multiplying when x changes by 5. So it takes 5 steps. If x takes 5 steps, I multiply times 1.2. If x changes by 5 years, I multiply by 1.2. So this is for delta x. Now, if delta x was 1, we would have b. But it's not 1. So it's really 5 multiplications of b equals 1.2, because I went from 20 to 25, and that took me to go from 20 to 25. I got 1.2 as my multiplier. So I don't have b yet. I can solve for b, but I don't have b yet. Now, down here I put up this little note. It's really easy if delta x is 1, because then you're going to have b really fast. But let's summarize what we just came up with here. So, in a table of x and y's, if you have a constant delta x, so it's counting by the same number, 10, 20, 30, 40, delta x is 10. In this case, 20, 25, 30, 35, it's counting by 5s. If it's 20, 21, 22, 23, it's counting by 1s. So you got to have the same x increment. And if you do, it's easy to tell if the data is linear or exponential. If the difference y2 minus y1 is constant, the same number every time, then you're going to have a linear function. If the quotient, that's just another word for division, y2 divided by y1. So for linear functions, you're subtracting the y's to check. And for exponential functions, you divide the y's to check. And if you get the same division every time, then you're going to have an exponential function. And just a little side note, this red box is telling you, oh, here's a shortcut. Right over here. You do the division, and if delta x is 1, then the division is equal to b. Now, it only works, the division only gives you b immediately if delta x is 1. But here, delta x is not 1. So we got a little bit of work to do before we can solve this problem. We're going to practice some of this solving later, so I think I'm going to move on from here. And let's proceed to exponential functions base e. There is this number e. It was discovered by a really brilliant, famous mathematician named Leonard Euler. Now, it's not E because of his last name, although it seems like it should be. But he said it wasn't. He just, he would discover a lot of important numbers, and he just was going down the alphabet. So he got to this number. It happened to be his E letter. It is an extremely amazing number. It's called a transcendental number, and it has some relationship to pi. In the world of geometry, it's like God has created geometry in such a way that wherever you look, pi is hiding somewhere in the world of geometry. It's just created into the order of how geometry operates. Well, in the world of growth and decay, which is particularly the subject of calculus, E keeps coming up. It's like God created the whole world of growth and decay around this number E. Everything you study that has growing principles or decaying principles or changing principles in it, E keeps cropping up. It is a fundamental number in the backbone of how the world is interpreted. So when you study calculus, you will see E everywhere. It just comes up all over the place. Here are a few interesting formulas that shows something changing. It's kind of growing. The first one there on the top is a really terrible, ugly looking fraction. It's an infinite fraction. It changes a little bit and keeps growing, and changes a little bit more and keeps growing. And if you run that fraction out forever, it comes out to this number E. There's this other thing called factorials. That's that third equation there. And if you, those are really special fractions, and you add up those fractions, and you add them up forever, it becomes this number E. This middle one is one that we would see more in pre-calculus. It has to do with the limit, though. The limit there is a calculus idea, but we've talked about limits as x goes to infinity. What does the answer go to? What does the y answer to? And the y answers go to this number E. So I put a little history blurb on there for you, but E is very unique. And so we're going to study this number E. Now that's just a round off. The decimal goes forever and it doesn't stop. But it is quite important in exponential functions. So let's begin to explore exponential functions base E. Now, what we have studied a few minutes, what we studied in the first half of this lesson was a function that was A. Now the A number is the same. It's the vertical stretch coefficient. But then our multiplier base was just B. Now we have a different multiplier base. It's that new special number, 2.71828. And the exponent is a multiplication of two things. This is the exponent. It is R times T. Now, so A is the same non-zero number. It represents the initial value. If we take the point 0A, that's our starting point. So 0A is our starting point. Just like exponential functions we studied before. But now we're talking about something called continuous growth. A continuous growth rate. And so what is the difference between these two? It's subtle and it's not going to make a huge difference for us. The green equation and this black equation over here will solve our word problems, and for the most part the black one and the green one are going to work relatively close together. But there are times when the green one is better and times when the black one is better. If you're just doing algebra and your multiplier is 1.2, the green one's better. But if you're modeling real life, the black one is better. If you're modeling something that grows by increments, like a loan, you're paying interest on the loan and the interest changes once a month or once a year. So it's like the interest payment is calculated, then it waits a whole year, and then it's recalculated. But if you're looking at the coronavirus, how fast is it multiplying? Does the coronavirus grow by increments? Does it wait a year before it takes a step in growth? No. Does the coronavirus wait a day before there's a step in growth? No. The coronavirus is growing continuously. And it turns out that function in the black box, the exponential base e, models continuous growth more accurately. So, when you're doing your Newton homework assignments, and it's about biology, it's about radioactive decay, it's about the population of a city, it's about a virus growing, it's about medicine metabolizing in your body, Newton is going to expect you to use the black equation, the continuous growth model. Usually on my test, if I want you to use the continuous growth model, I will put the word continuous growth in the word problem. And so if I don't put the word continuous growth in the word problem, you can use the green equation and just do regular exponentials. Okay, so there's some ideas there. Otherwise, it's going to be very similar. It grows exponentially, something like that. That point there is 0a, and so we have a horizontal asymptote at 0. That's our horizontal asymptote. So those two things, the graph, the asymptote, the starting point are all exactly the same as the standard exponential function we studied before. Let's look at some examples. Now, we've studied this question number 1 with a slight difference. It did not say continuous growth. So, with continuous decay, Einsteinium, this radioactive chemical, is decaying at a continuous decay rate. Now, for all practical purposes, the radioactive material, it is better for us to think of it in terms of continuous decay. When we did it before, we weren't really using the most accurate model. But because it is continuous decay, we're going to use, I'm going to use the same variables that we did before, E and T. This is T for days, and this is amount of Einsteinium. But this time I'm going to use the continuous growth model, A times E to the RT power. Okay, now let's pull out some information here. The starting value at 0 time, we had 10 micrograms. So we have A equals 10. We also have a daily continuous rate. R equals 0.03. Now I should have put on there that R is negative because it is decaying. So that's an important aspect of excuse me. We have a negative decay rate. Well, we're done. As far as building the equation, it's built. So that was our first step, was to build the equation, and the word problem gave us everything we needed. The initial value is 10, e to the minus 0.03 times t. That decimal is not coming in very nice. 0.03 times t. That's my exponent. Okay, now we can answer the question. So, the time is a week later, or 7 days. So we just got to plug that in. So E equals 10 times the number E times negative 0.03 times 7. And now the rest is calculator work. So I'm going to pull up the calculator here. Wow. That freaked out there. It's freaking out more. Okay, let's do this calculation here. Now, there's two places you can find E, but down here, above the natural log is the e to the x. That's the exponential base e to the x power. And that's the problem we have to do here. We have to do 10 times. I'm going to hit second and then hit the log button. See the log button in red? But since I hit the second button first, I'm activating the command above, the e to the x, and that's what it has. Now, if you have the old operating system, you're going to have parentheses there, and you're going to have to type in the exponent with parentheses. But this has the nicer print, so it looks better. 0.03. Now, I can't put t in here, but I'm taking t out and plugging in 7. Oops, times. It is times 7. And I hit that calculation and I get 8.1. Now, I don't know if you remember the calculation we did before. We got 8.008. And this came out as 8.1. This one is a little bit more accurate. It's still a round off though, because e is irrational. That decimal will never stop. But we can say more accurately, because of the continuous growth equation, that it's 8.1 micrograms of Einsteinium 253. All right, let's look at another example. So you wake up in the morning and you grab a cup of coffee, and it says that the caffeine, now the caffeine's in your body, and your body's using up the caffeine. Now, does the body use up some caffeine the first hour and then wait? And then your body says, okay, an hour later, I'm going to go get some more caffeine. And then the next hour, does it wait for each hour to use caffeine? That's what I mean by incremental change. Every increment of an hour or every increment of a minute. But no, caffeine isn't behaving that way. Caffeine is continuously being metabolized in our body. So the equation we're going to need for the caffeine is a exponential base e, the continuous growth model. So let's figure out our variables. Let's let C equals the amount of caffeine. And we're going to let T equal the hours. And we're going to use the model, not E, I was using Einsteinium again. Caffeine equals A times E to the RT power. Okay. So, notice that we have the 17% per hour, the continuous rate again. So the continuous rate is what told us to use base E. And the 17% per hour, that's our rate. Now it is a negative 0.17 because we're losing, the body is losing the caffeine. It's using it up. Okay, there's a question. How much caffeine is left in our body after 8 hours? Okay, we need some more information. Now, we need the starting amount. And it says after drinking a cup of coffee containing 100 milligrams. So when we started our first sip of coffee, we had 100 milligrams of caffeine in that cup. I shouldn't say that when we first sipped it, but when we finished swallowing it, that last drink of our coffee put all 100 milligrams in us. So we have enough to build the equation. First step. 100 times E to the negative 0.17 times T. That's my exponent. Next, we have a question to answer. T equals 8 hours. So, started in the morning, 8 hours later in the day. How much of that caffeine is left? We're just going to plug in 100 E to the negative 0.17 times, and we're going to plug in the 8 hours. And the rest is calculator work. Okay, you can see I typed in 100, that's the initial value, times the exponential function base E, raised to the negative 0.17 power times the 8 hours. And when we calculate that, it says 25.666. So 777, that's an interesting collection of numbers there. Let's round that off to, say, approximately 27 milligrams, 26 milligrams. So C is approximately 26 milligrams of caffeine. And as I recall reading somewhere, when your body has around 20 milligrams of caffeine, you virtually don't really notice the caffeine effect anymore. So anyways, that's just a little side tidbit there, but we use the continuous growth model to come up with this calculation. All right, we're also going to look at continuous growth models just a little bit in the world of finance. Now, this is not a high priority for me, but it's good to be exposed to some of these formulas. And I think your Newton homework will give you one or two of these. And so I'm not going to make you memorize these formulas. If we do a finance problem, I will provide you the formula on the test. You just need to know how it works. So first thing here, I want you to pause and fill in all the blanks. So pause the video and fill in all the blanks where I'm describing the variables and the parameters in the equation. Okay, now that's taken care of. Let's detail out this just vocabulary a little bit. So if you put money in the bank, that's going to be the amount after a period of time. We're going to make a function. So your money in the bank is growing, and the amount of money grows with time. So the amount depends on time. We're going to have a function of time. And of course, T would be years. So if you keep the money in the bank for 10 years, your principal is your starting investment. So you put $1,000 in the bank at the beginning. How much will you have in 10 years? So the 1,000 is your principal. R is the annual percentage rate. Your account is going to be promised by the bank to grow at a certain percentage, like 2% a year. Unfortunately, that's a terribly small percentage. Some investments can promise more, like 4% or 6%. Those are really nice. 8, 9, 10%, those would be great. They're guaranteed, but I don't think those are easy to find. So you're going to have an interest rate that is calculated. And then N is the number of compoundings. So sometimes they elect to pay you once a year. So they calculate the interest you earned only once a year. So N would be 1. But sometimes they calculate the interest you earn biannually. That means twice a year. So N would be 2. Or sometimes they calculate it quarterly, which N is 4, or monthly, N is 12. Or sometimes they calculate it daily. You calculate your interest earnings every day, and N would be 365. So you got to know what those compounding numbers are, and each of those values have a place in the formula to plug in. Now the next step above that is, well, what if we're compounding not every quarter, not every month, not every day, not every minute? What if we're compounding every second? Or that's like saying we're compounding continuously. Well, if we're compounding continuously, it becomes the base E equation. And so sometimes that situation is the best model. Let's look at some examples of these guys here. Okay, we're depositing money in an account. So the 4,000 is the principal. The interest rate is 0.066%. The compounding, that's the compounding quarterly. That means N is 4 times a year. And the investment is in the bank for 5 years. Now, this function is our equation for calculating the amount of money that we are earning. And so at this stage, it's really, what's the amount of money? It's really just a matter of plugging in. So P is 4,000. 1 plus R is 0.06. Divide that by 4. And then we're raising it to the 4 times 5 power. And so I'm going to have to shrink this so I can do the calculator. Let's grab the calculator and find out how much that money turns out to. So at this stage, the rest of this problem is 100% calculator work. So once you got the formula in front of you, you just plug in. 1 plus 0.06 divided by 4. Close the parentheses. Then we're going to raise that to, remember that was 4 times 5? So I'm going to just put in 4 times 5, which I know is 20. 20 power, hit enter. And so the amount of money has gone to, after 5 years, the amount of money became $5,387.42. So that's not a bad return after 5 years of having your money in the account. Okay, I got one more of these. I've got 2 more, but I'm just going to do 1 more. Okay, let's go to the bottom one. In the bottom one, it says we're looking at a deposit, same amount of money. The account is paying 6%, the same percent, but it's compounding continuously. So notice the continuous word in there, which means the best model is this one here, the exponential base E. So let's get that one set up and starting that one going here. And so on this problem, we have a lot of the same things. 4,000 is our principal. The percent is 0.06. Time is 5 years. And our formula for the amount of money is principal times e to the RT power. So we're just going to plug in 5 years. And we're plugging in the principal of 4,000 e, and we're going to multiply the rate times the time. 0.06 times 5. And now we're just doing calculator work. So we will have 4,000. I'm going to activate the exponential function above the log ln button. So I've got to go second, see the red second. Now I'm going to push the log button, see the red log button. That activates the exponential base E command. And I'm going to put in 0.06% times the 5 years. Hit enter. And notice the 5 years compounding continuously earned a little bit more money than the one we had before. It's like, it's more than $10 more compounding continuously. So you do get better returns if you can get continuous compounding. I'm going to call that 44 cents. So there is the amount of money we've earned. Okay, so we've seen several examples now of the exponential base E equation. Study hard, practice on lesson 6.1, and I will see you back in class.